So, directions here. I talked about the Vesper theory part on Tuesday, so now we're going to look at the valence bond theory part of the worksheet. You're going to base your valence bond theory on your Vesper theory part, so we have to have that done first. The number of electron groups tells us what orbitals will be hybridized. So if we have 3 groups, we need S and 2 P's. If we have 6 groups, we need an S and 3 P's and 2 D's. So you start with S, you go into P, and then to D if you need to. Just take as many orbitals as you need for the number of electron groups on your central atom. For the central atom, you need to take into account any formal charges. So if it has a negative formal charge, you need to put an extra electron on it. If it's positive, you need to remove an electron. You start by drawing the unhybridized orbital diagram with the valence electrons in it. Then you draw the hybridized orbital diagram with the electrons in it. For the non-central atoms, we are going to assume that they do not hybridize. So we're just going to draw regular orbital diagrams. Again, you have to consider any formal charges. And then the orbitals that bond will each have 1 electron in them. And so you're going to write the bonding descriptions. Sigma comes from overlap of hybridized orbitals on the central atom. Pi bonds are from unhybridized on the central atom. So let's do NO2 minus. Why is it not showing me this whole thing? My computer is just not cooperating here. There we go. Okay. So we have to start with the Vesper theory for NO2. So hopefully you've got this done on worksheet 10. And there's our Lewis structure. So from looking at our Lewis structure from worksheet 10, then we can fill in the Vesper theory stuff. We look at the number of electron groups in the central atom. There's a single bond, a double bond, and a lone pair, so that's a total of 3 electron groups. Number of lone pairs on the central atom is 1. And so from that, we can look at the electron geometry. So for 3 groups, it would be what? We've got linear, we've got trigonal planar, we've got tetrahedral, trigonal bipyramid, octahedral, bent, angular, seesaw, T-shape. Anybody? How do 3 balloons get away from each other? It's trigonal planar. So 3 electron groups tells me trigonal planar. 1 lone pair tells me that one of those is invisible, and so the molecular geometry is going to be bent. And then the perspective drawing, I don't expect great artwork here, but I want to see that you've tried. So here I've got my nitrogen in the middle, and this is going to be bent. So I've got an oxygen over here, and this is a double bond with that one, and then the other oxygen has a single bond, and so the bond angle here is less than 120. And if you want to, you can show the lone pair out here, but it's not necessary. Okay, so once we have that, then we can do valence bond theory. So orbitals used in the hybridization, that's going to come from the number of electron groups. So there's 1 s orbital, there's 3 p orbitals, there's 5 d orbitals. The number of electron groups, you start counting here, and you move along. How many do we need? We need 3. sp2. So that's our hybridization. Here it's asking for the number of valence electrons on nitrogen. How many valence electrons does nitrogen have? Well, it's got 5, right? And so we can draw nitrogen's orbital diagram. This is the unhybridized. And you can draw this vertically or horizontally, kind of up to you. Here's S and here's P. And those 5 electrons would go in 1, 2, 3, 4, 5. For the hybridized orbital diagram, we're going to take the S and 2 of the P's and combine them into 3 degenerate hybrid orbitals. And then we've got 1 p orbital left. We have to put 5 electrons in there. 1, 2, 3, 4, 5. And then it says, circle the lone pairs. There's my lone pair. This matches up with the 1 lone pair that I see. Now, there are 2 different oxygen orbital diagrams here because these 2 oxygens are not in the same situation, right? One has a double bond, one has a single bond. And so we need to think about the formal charge on those guys. This oxygen here has a -1 formal charge. The nitrogen and the other oxygen are 0. So this is the NO minus bond description, and so here I'm going to use the orbital diagram for this oxygen. It gets a little bit small, but so oxygen normally has 6 valence electrons. If it has a formal charge of -1, that means we add an electron. So this is going to have 7. 1, 2, 3, 4, 5, 6, 7. And then the bond description for that, we're going to take this half-filled orbital and it's going to overlap with one of these. And it's going to make an N. It's a single bond, and so it's going to be a sigma bond. And on the nitrogen, we are using an sp2 hybrid. And on the oxygen, we're using a P. Let's label it S and P. The other oxygen has a 0 formal charge, and so it has the regular number of electrons, which is 6. So this oxygen has 2 half-filled orbitals, and that works out well because it has a double bond, so it needs to make 2 bonds. One of these will overlap in a sigma bond with the hybrid orbital on nitrogen. So you always have a sigma bond. The nitrogen is using the other sp2 hybrid, and the oxygen is using a p orbital. So we've used this electron. Actually, let me do this. So I took that electron and overlapped it with this orbital. And I took this electron and overlapped with this orbital. And so what I've got left is this one right here, and that's going to overlap with the unhybridized p orbital. That's going to make a pi bond. The second and third bonds are always pi bonds. So this is between nitrogen and oxygen. On the nitrogen, I'm using a p orbital, and on the oxygen, I'm using a p orbital. And there you've got it.